Alrighty.
Make sure this all comes through okay.
Alrighty.
Right, make sure this... Yep, it does. Alright, hello crew. Good, what's today? Friday? Happy Friday. Not me already losing my mind. Good start. So, this is, of course, a bonus stream. Usually we are not here on Fridays, but, because we had some stuff going on earlier in the week, I said that I would move the Galactic Curiosity to today. And this was actually one of the crew requested discussions. Was actually a talk on quantum computers. So last week we did a little bit of a dive into AI because there's a certain crew member who's going to be joining us here soon. Unfortunately, she is still in repairs, so it's going to be probably another week until she can join us. But last week we talked about AI. And part of the AI discussion is what is the probability that once we have quantum computer working, that AI will get crazy. And so I thought it'd be kind of a cool one just to like dive into quantum computers this week. Just talk about it a little bit, so like what's out there right now, because this is very, very new. Like this is some cutting edge stuff that like there's 3 main companies working on. I know Google's one of them, IBM. And then there was a third one that I actually don't know if I wrote the name down for, but there's those 3, and then like Intel's working on some stuff, but like those are the 3 big players right now. So let's go ahead and jump into it. So what actually is quantum computing? So it's basically like real world science fiction. There's a bunch of different things going on at once. So in a typical computer, you have a bunch of ones and zeros. And as the computer thinks, it has to think on if it's either true or false, 0 or 1, or, you know, how that goes. But that's not true with a quantum computer. What a quantum computer does is it actually uses atoms to, like, it sends like lasers at these atoms and tells it to think for us. And, like, depending on how these lasers, or how the atoms react to the lasers, it comes up with an answer. And that just sounds so wild. Like that is just so out there for me. And but that's how it works, is that these atoms, we're given a question, like we're given a math problem, and we give it to the quantum computer, and the quantum computer will do all these different simulations at once. And where a computer would do ones and zeros to arrive to its answer eventually, what a quantum computer does is it looks at every answer at once. Like what all the answers could possibly be in every situation that could possibly exist. And then as these answers are coming through the system, there's probability weights. So each qubit, which is what these quantum computers are acting upon, each qubit sends out a wave. And these waves can cancel each other out. And like by canceling each other out, that means that they're wrong, or they can build on themselves, and that would lead us more towards a right answer. And so that's kind of like how they work in general, but we'll kind of get more into that in a minute. So, and this is kind of what I was just talking about. So on the... Hey Kazuri, welcome to the stream. So what makes it special? So qubits are kind of like regular bits, but they can be 0, 1, or both. So I thought this was a really cool image on the right, where like I was saying, a bit in classic, how computers work now is 1 or 0. Like they have to either look at those 2 options, and then there's tons of zeros and ones that make up everything you see, everything that goes on. And that's how all the decisions are made in a computer, which is like really crazy if you get down to it. There's a lot of ones and zeros going on, and it just makes everything work. A qubit, though, is looking at 0 and 1 still, which is still true. However, it also looks at what's called the superposition, which is any possible combination of 0 and 1 in any point in space. And what I thought was a really good kind of way to understand this is imagine you take a coin, right? And you throw it in the air, you flick it in the air, and it's spinning through the air. And we both know, I know, and you know, that there's going to be heads and tails, just because we know how a coin is. But until we see it land, we don't know if it's going to be heads or tails. So we don't know if it's going to be that 1 or that 0. So it's in a state of superposition until it actually finally lands. And it's actually by it landing or you making an observation on the superposition state that it then coalesces into either 0 or 1, heads or tails. And so, like, imagine there's like a bunch of these things going all at once, and this is how every path is determined, every solution is, they're able to find a solution, is there is just all these qubits that are spinning in the air, and we don't know which one's going to be heads or tails, but because there's a lot of them, it'll make, it'll find the right answers. It's so weird. But, so each qubit also has more possibilities. So, we have 0 and 1 in the superposition of between 0 and 1, which, I mean, you can see in the sphere, there's a lot going on. It's called a block sphere, by the way. But, and there's a lot of things going on. The more qubits that you have working together, then the more possibilities there are. So if you only have like 1 qubit, you have a limited amount. You have a pretty high amount, like, don't get me wrong, but you have a limited amount of paths that it can go down. But if you start to combine more and more qubits, you start to get more and more possibilities. And it literally gets ridiculous, and I'll prove that in the next slide. But one thing is kind of challenging with these things, though, is that for them to work, they have to be at almost absolute 0. Like, like Kelvin, like the whole absolute 0, which is incredibly hard to do. Extremely hard to do. However, let's say you had like 300 qubits, right? Just, 300 of them, which is possible. One of the companies that is making these has 5,000 in one of their quantum computers. Just 300. And you would have more possibilities that you could use to solve than there are atoms in the universe. It's 2.037 times 10 to the 90th power. That is crazy. 300 qubits. More atoms in the universe. Like, it's so wild. So, one of the things that I mentioned was superposition, and I kind of mentioned interference as well, but I will start with superposition. So if I go back to superposition is where the line on that sphere is just going crazy. It's just freaking all over the place. That is that's the coin example where we know it's going to be either 0 or 1, but until it lands, we don't know which one it is. We can't say for certain that is going to be heads when it lands, So that's called superposition, the state in which something exists between 2 known states or many known states. Interference is kind of what we're talking about, where we're talking about with qubits being waves. So interference is saying that, let's say we have an answer, right? Let's just take 2 plus 2 as an example. Let's say we have an answer that we want to get to, and we send this formula into our quantum computer, and it starts doing the calculation. Well, there's going to be some qubits that'll say 2 plus 2 is equal to 5. And that's wrong, right? So those ways will kind of interfere with each other, and they'll start to cancel out. 2 plus 2 equals 3, 2 plus 2 equals 1. Things like that, they'll start to interfere with each other. They'll cancel out to where we know that those are the wrong answers. But then you'll start to get the other qubits that are like, okay, well, actually, maybe 2 plus 2 equals 4. And now those ones are right. So now you're going to get all these different qubits that are moving down the path. Some ways are canceling out. The ways they're canceling out, we know those are the bad answers. The ways that are boosting, we know those are good answers, until we arrive at the point that we have our answer. And once we can measure our answer, that's how we get the final, that's how we determine that 2 plus 2 equals 4. And we'll get into observation here in a moment as well, but that is how interference works, is those waves are crashing into each other, boosting each other, canceling each other out. Find the right solution. And this one, I'm not gonna lie, this one confused me so bad. Like, with each of these, like, Galactic Curiosities, there has been something that has just thrown me off that I just couldn't, like, I literally sat there for, like, hours on end trying to figure this out. And this is gonna be it for this discussion, because entanglement, I think, is so confusing. So, entanglement is saying that if you have 2 qubits, right? So you have qubit A and qubit B. You can entangle them, you can mate them together such that whatever happens on qubit A also happens on qubit B. And what's kind of interesting about this is that these 2 qubits could be galaxies apart. Like, galaxies apart. And so I was like, wow, that's kind of crazy. Like, could we use this to do like a... Yeah, so on, so Almighty, welcome back first of all. But, every Thursday, we do a little bit of a deep dive into like a Galactic Curiosity. So cool stuff that are out there. We talk about either some space stuff or like some cool stuff on Earth. And it rotates. So we talked about like the ocean and we talked about like black holes and everything. So that's like every Thursday. But since we were able to do it yesterday because, yeah, we were trying to take down, you know, the Titans in Subnautica, we moved it to today. But, what was I talking about? Oh, yeah. So they are, oh, I'm glad to hear it, Kazuri. I'm glad to hear it. But, so they're like galaxies apart, right? And what I was saying is, like, could we do like some sort of duplication glitch? I don't know, like something weird to where if we took like qubit A and we put energy into it, would energy be received by qubit B? Because it's, if they're, you know, if they're acting the same, they're behaving the same, and they're reacting the same, does that mean that if we do something to one, it behaves the other? And it's not. That's not how it works. It's basically saying if you have two coins and you have them, like, it doesn't, the distance doesn't matter. But like if you throw them both in the air and let's say one of them lands first, like one of you know, you observe one of them, so you know it's heads. That means no matter what happens, the second coin that's in the air is going to be heads. So they will share the same observed value at the end. And in another one I thought was really cool, another example, like getting away from coins, one example is dice. So if you have two dice and you roll them and like one of them lands on 4, the other one's automatically going to be 4. And so I was like, okay, well, this is interesting. Like, what is this used for? And in math, there are like logical gates that you can do, and that's like how computers can operate is, you know, there's and, or, nor, or, like things like that. And this is what those are used for. The entanglement is how they do logic gates with quantum computing. And I'm like, oh, this is getting a bit, it's getting a bit above my head. But it is really interesting that they can actually do stuff like this. And it's just like, the fact that it's out there and this is real science. Like, this isn't even like theoretical. Like, this is happening today. And it's like, oh my gosh. So let's talk about observation. So now we talked a little bit about like how superposition works, where you launch a coin into the air and we don't know what's going to be. It's going to be either heads or tails. And observation is the act of determining the answer from, you know, the superposition. So how they do that, and this is like kind of this image here, is they actually launch a photon, or, you know, a light particle, through a tube at these qubits. And what that does is it's a physical interaction. So the light photon will hit the qubit, and because it interacts with the qubit, it will give it's like, okay, I'm getting smacked. I have to have a value because you are interacting with me. And so that is what actually makes the qubit collapse to a value of either 0 or 1. And I'm just like, okay, that's really cool. But one thing I thought was kind of cool whenever I was researching this is another way you can think about it is that in the quantum world, things don't exist necessarily until you look at it, basically. So imagine like a video game. So you're staring straight ahead, like let's say Subnautica. We're swimming through the ocean straight ahead. We're swimming. Everything that's behind us, everything that we're not looking at, isn't there, right? It's just because we live in that world, we know it's there. Like, we know in our mind it's there, but there's no way to prove it's there unless you observe it. But the thing is, by observing it, you're making it reality. You're making that the 0 or 1 collapse to a value that is known. And so I just think that's really interesting, is like, you don't know, like, if even sitting in your seat right now, you don't know there's something behind you unless there's a stimulus saying that there's something behind you. And I don't mean to give anyone like existential like dread or something, but is like, it's just, I think this is really interesting. Like, the quantum world and the quantum like mechanics and everything are so interesting because until something is observed, there's no way to prove it's there. So I think that's really cool. And there's a wild Mira in the chat. So one of the things that I think is kind of a common misconception, and this is actually something that I had as a common misconception, and I'm kind of sitting in front of it, so I apologize. I'll explain it still. But quantum computers aren't going to be like an end-all once they're common. So they are good for certain things, don't get me wrong, but they're not good for everything. So what are some of the things that they're good for? Is if we ever wanted to discover like a new element or discover like dark matter, something like that, something that is out there in the universe that has formula for it that we can apply math to and start to solve, that is what a quantum computer is good for. It's taking those problems and basically applying, all the known possibilities to those problems to try and solve the issue. And they're really good for that. That is literally like what their purpose is to solve these really complex mathematical equations. But they're also really good for optimizing complex systems. So maybe there's something that we're looking at that is just, we're making it hotter than it is. Maybe there's a better way to do it, and it's like optimizing those systems. It will find the best path possible. So in one example of like what I was looking at is like, let's take a game right now. Like on a normal computer, let's take a game, and let's say it's running at 60 FPS, right? So, and then you sit next to a quantum computer running that same game. How will they play? So the normal computer, as we all know, it'll run, but you interact with it. And let's say you're trying to get to the end of a level. You take your time, you puzzle through it, you get to the end of the level, sure. What a quantum computer does is instead of, someone actively participating in it, what it does is it looks for every possible path from where you start to the end of that level. It will find the path that you deem to be the best. So you have to give it some sort of criteria. So let's say it's like, you want to get to the end of the level as fast as possible. So it will search through every single possible path through that level till it will be like, okay, this is the path. But the thing is, whenever you go to observe what it's doing, you won't see it doing all these possible paths at once. You'll just see the final path. So if you were to put these two computers right next to each other, the quantum computer would literally go straight for the most optimized best path. But behind the scenes, it's doing all the paths at once. All the possible paths that it could find in existence for that game. And so that's like also crazy. So speedrunning is gonna basically go away whenever they come out with quantum computers. Did you go to college for this? No, I literally just learned about this like today. Like, I'm not gonna lie. I have a lot of fun researching these topics and like getting into them. So it's always really neat for me. For like research though, I know this is kind of what the topic actually began with, was that someone was asking if, I think it was actually HK, it might have been, but someone was asking, once AI, once we have quantum computers, hey, I appreciate it. I try my best for you guys. Once we have quantum computers, will AI become crazy, right? And it's because AI, what it does is it has I don't know who was here for the discussion on AI, but basically, like if we're talking like ChatGPT, right? A large language model. What it does is it has all the words in the human language. And it'll take those words and it has weights that it applies to them, such that whenever you ask it, what sounds good for a healthy meal, right? It'll be like, okay, well, I know that these certain words are weighted such that a healthy meal would be the correct response. And it'll go through all those different steps to get you the right response. Well, now once we have quantum computing, now imagine, instead of like waiting, I don't know, like a couple seconds for, I don't know, just like an example, just like if you ask a question, just waiting a couple seconds to get that answer. Literally, a quantum computer would be able to boost it to be even faster. It would be instant. Like, there would be no loading, there would be no anything, it would be instant. And then especially like if you start to get into things that are like higher complexity, so you're starting to get like heavier code, you start to get into like building things, huge data analysis, it would be instant and it would be crazy. That said, it's not going to be it's not going to become like a godlike being just because there are still limitations, because AI is trained on data, right? So it has to go through all these different iterations to get where it needs to go to where it becomes the best model possible. But where a quantum computer is not trained on any data, it's actually, it's all those ways that we're talking about and the formulas that are put into it. So if an AI is looking at the past to learn for the future, the quantum computer is looking at what we supply it and solving for the future. So, I mean, don't get me wrong, these things can still be integrated to each other. And, like, I'm sure that's going to get insane. Like, the AI, when quantum computer comes out, I'm sure it's still going to be insane. But it's not going to be essentially like, you know, the mega mind, like, of what it could be. So, there's a little bit less of a concern than I thought there originally was. But that's, you know, take that with a grain of salt and always be ready for the robot uprising. But that said, there are still some things that, like, quantum computers will be great for. So, like, everyday task of, you know, just working through spreadsheets, getting things done on your computer that may require not so much of, like, heavy, complex system solving, but, like, things that you need now, things that you have available now. It's not really good for that. And it's not built for that. Like, you can't, like, open it up and start typing on it. That's not really how it works. So it does have its limitations, but it's incredibly powerful for what it's used for. Like, I mean, and I will say to kind of expand upon that, even today, quantum computing is still very early, right? Like, a lot of the supercomputers that we have on, like, around are still way outperforming the quantum computer. So it still needs to cook, but it's definitely, I feel like once it comes around, it's gonna be incredibly powerful. And, oh, I actually just talked about this. So what I was talking about is, like, AI learns from data. Well, quantum simulates that data with, like, formulas, or in this case, physics. An example of quantum is, like, if one of the things I know, but we're probably going to want to do is, like, it'll help us solve dark matter. So in space, most of the universe is actually made of a matter that we can't detect. And because, like, maybe we'll get into that in one of these Galactic Curiosities, but there is evidence that suggests that there is something acting upon bodies in, you know, the cosmos that isn't something that we could physically see, something we can't detect, like gravity is. It's not gravity. It's, you know, there's something out there. So one of the things that we could use a quantum computer for is that we can actually use, like, the formulas that we have, because we have these formulas today, we just can't solve them. But we could plug that into the quantum computer, you know, encode them on the qubit states and have it run, and we could get that answer. And that would change, I'm not kidding, that would change everything. Like, that would solve, we could possibly start finding dark matter. We could possibly even start, like, collecting dark matter, depending on how challenging it is. And there's already ideas of, like, a dark matter warp drive. You know, like, these are the things that could bend space-time. Like, this could literally set us into the spacefaring age. Or I should say, set you guys in the spacefaring age. I landed here. So, but we're all well on our way. And I think that's crazy. And then kind of what I was saying with, like, the ways earlier with the interference is that quantum will explore all the paths available. So if you're, like, walking to a forest and then that forest splits into, like, 20,000 paths, you could be like, okay, computer, can you please tell me which is the best way and the safest way home, and then it'll highlight it for you. And I think that's pretty cool. And the way I kind of looked at it was like, it's like an explorer. So the computer will make 20,000 copies of itself, and it'll head out and look at all the different possibilities and be like, all right, I'm coming back. I'm going to let you know this is the path. This is the safest path. So that is kind of neat. One of the challenges, though, is that they are very, 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 they being qubits, are very temperamental, very hard to use, because what a qubit actually is scientists are taking atoms, and they were basically making those atoms, like, stop moving. And to have an atom reach a point that is basically not so much at a standstill, but pretty close to a standstill, is that they need to be at absolute zero. And so that's incredibly challenging. So now you have to take heat and temperature and all those things into consideration whenever you're doing this quantum computer. And if you lose that temperature control, then everything just goes down the drain. Basically, it's gone, because if you can't control the state of that atom that you're encoding upon, then you can't do anything with it. It is just bad information, and that's called decoherence. So, and there's two other ways that decoherence can happen. So one of them is called quantum noise, and it's just basically that whenever you're encoding upon a system, and especially nowadays, early on in its development, there is going to be a lot of overhead error. So whenever you're actually trying to solve problems, there's going to be a certain percentage of error that as you're going along that could build up, and that buildup could make a solution also useless, because there's nothing you can do with it because it's just error prone. So and then the last one is that over time these qubits can also become destabilized, and whenever they become destabilized, then that can also lead to decoherence. Now, unfortunately, if they do become decoherent, then the only thing you can do is reset them, put them back into that stable state and restart over. So any information that was encoded onto that qubit is gone. It's just completely gone. There's nothing you can do to get it back. So that is pretty tough. But one of the things I'll kind of end with here is that at least for now, quantum computers won't replace classical ones. There's still a lot that classical computers can do that quantum computers just aren't built for. But what they will do is that they will solve different problems in a lot of wild new ways. So once they're out and this becomes kind of a commonplace, it's going to be really interesting to see the solutions that come about because of it. And I'm pretty excited for it. It's going to be really interesting. It's definitely something I'm going to be keeping my eye on as new developments come out. See what they do with it. But do you guys have any questions? Any questions from the crew about anything?